pleasure to be here. My name is Francesco, and I'm a Marie Curie Fellow at the University of Padova. And when my talk was accepted, I was asked to give an introduction to quantum batteries, on quantum batteries to a broad audience. So today, the outline of my talk has changed a little bit from the abstract that I submitted. And the idea is that I want to give you an overview of this topic and the current research directions and how maybe they can interface with the Quantum Energy Initiative. And so I want to begin by saying that when we talk about quantum batteries, the idea is that we want to go from a classical picture of metastability to a quantum mechanical one, and to see if this change of perspective brings any new knowledge on energy storage tasks at a fundamental level. And of course, the emphasis for me and for a lot of the people that work in this field is on the many-body effects and the scaling of the system properties with the number of subsystems involved, to see if things like coherence, entanglement, delocalization can be exploited to get some form of enhancements in properties like charging power, energy storage, lifetime of energy, the stability of the charging process, and so on. The sort of research area stem from this key research question, quantum thermodynamics. Is there any form of quantum advantage in this field? And interestingly, in 2015, it was shown by Binder and collaborators that entanglement generation is linked to super extensive power scaling when you compare the dynamics of a system that evolved collectively with one that evolves sort of locally. And so this observation has been since the main driving force for research in this area. But there have been a lot of different interesting insights and development beyond power scaling, such as the precision and work fluctuations during the charging process, and at the end of it, the protection from energy loss when the system is coupled to an environment, and recently also some experiments to test some of these ideas. So today I'll begin with an overview of quantum batteries. I want to tell you what they are and what the main research questions are and their motivation. And then I'll tell you about some of the current challenges and outlooks. I'll briefly talk about one research project that we've recently done on the wave, on the precision of the charging process, and then I'll wrap it up summarizing some of the key takeaways. Okay, so what is a quantum battery? It's a very general thing. Almost everything is a quantum battery in the way we envision it, so to say. It's just a quantum system with non-degenerate energy levels, so it can store some energy, and that can develop coherent superposition between its states and possibly also correlations, also quantum correlation with other subsystems. For example, it can be spin half in magnetic field, but also fluorescent molecules, atom in a cavity, superconducting qubits, cavity modes themselves, and so on and so forth. And today, the main focus of at least the first part of the talk would be on the ideal case of charging the quantum battery with a unitary, a cyclic unitary operation that is ideal, reversible, is entropic, and can generate coherence between the subsystems. And I want to do this to discuss the relationship between power and entanglement. In practice, obviously systems are connected to an environment. They lose energy because they're not perfectly isolated, and they also undergo decoherence. So to talk about energy storage, we just want to make sure that we are also saying that the relaxation times should be long when compared to the charging time and the work extraction times. And this whole thing is framed usually in the context of non-equilibrium many-body quantum systems. Some of these things we've seen before today already. And it's studied with techniques, with a variety of techniques from tensor network, quantum optical control, metastability of open quantum systems, and so on and so forth. Okay, so with this in mind, let's have a look at the relationship between power and entanglement. So obviously to talk about entanglement, we have to look at many-body systems. And so the first question was sort of asked by Alice and Fannes in 2013. It was, can entanglement help with extracting the optimal amount of work or injecting the optimal amount of work into a quantum system if we start from some separable state? That doesn't have to be a collection of a product state of perfectly pure states. It can also be a separable state or a product of locally mixed states. And it turns out that in general, Not obviously in specific cases it's possible, but in general, local operations are not enough to inject the optimal amount of work. So this was very interesting, and it led Alexandre Foray to suggest that perhaps entanglement is necessary to inject the optimal amount of work or extract it, because at least two-body operations were needed to do this. But later that year, it was proved that entanglement is not necessary. Two-body operations are necessary, but you don't necessarily need to produce entanglement along the way, because you can always take a longer separable path to connect the initial state to its optimally charged one. So this was very interesting. And it was the first hint that entanglement generation might rather be connected to power rather than the total amount of work that can be injected or extracted. And this was shown later in 2015 by Binder. And we can use a very simple example here to understand this. We can take an ensemble of n spin half system, all in the ground state, and we want to flip them to their local excited state. Keep in mind that we have a local Hamiltonian, a local internal Hamiltonian, where there's no coupling between them. And we can find the optimal local Hamiltonian to charge the system, to inject n times the band gap between the energy gap of each individual qubit, or the global optimal driving Hamiltonian. And if we put an energy constraint, whichever one you prefer, you can use the standard deviation of the Hamiltonian, but you can also use the operator norm or the Hilbert-Schmidt norm. You can show that the power of the local Hamiltonian grows extensively, whereas the one of the global Hamiltonian grows super extensively. And this can be also interpreted as an energy-efficient shortcut through the space of states. So here you see like a local unitary orbit, obviously the geodesic on the Bloch sphere. Whereas here you see the projection of the orbit on the total space of states that looks like some form of open dynamics, obviously, because the system becomes entangled along the way. So these are the solutions for this specific case. It's a simplified case. And this can also be seen as a shortcut in energy eigenspace. In this case, we're only connecting two states to each other, so we're skipping all these eigenstates. In this case, we go through them smoothly. So the question is this a quantum advantage, or is this just some form of like collective property of the system? And there's been a lot of work on this to try and understand whether or not these speed-ups can be attributed to the generation of quantum correlations, or they can just be obtained with classical many-body systems due to the collective effect. And now we have ways to detect the difference, mostly thanks to Andolina's and Julia Farah's work, but also a lot of other interesting contributions. And so here I just want to basically, like the takeaway is that we've got both quantum speedups that are associated with a strong entanglement generation and a shortcut in energy eigenspace, and collective ones that do not rely on entanglement, and they can also be seen in classical systems, and don't have any shortcut in energy eigenspace typically. So since 2017, there's been a lot of work to find systems that can have this type of properties, this type of power scalings. We've seen a plethora of ideas from spin chains to collisional models, quantum critical point models. But I like to sort of reorganize them into categories. For me, it helps both understanding how to implement them, but also how to find application that might be interested for those specific platforms. So usually I divide them in quantum platforms and quantum enhancements, quantum speedups, and collective speedups for cold, coherent platforms like trapped ions, cold atoms, and superconducting circuits. And on the other hand, we would have collective speedups that can be seen on noisy room temperature platforms like organic microcavities, MV centers, and so on and so forth. So I don't know if I have a lot of time, but I'm going to skip most of the part about collective speedups. I think maybe the Quantum Energy Initiative is more focused on coherent platforms, but really rapidly, what I wanted to say about collective speedups is that one of the most prominent models is the idea of seeing this type of speedups in a Dickey battery, which is based on the Dickey model, where there's uncoupled atoms or molecules that are all embedded in a common cavity. And these are collective, these produce collective speedups. They have a square root of n enhancements in the charging power, in the absorption power, but they are not really linked to a shortcut in energy eigenspace, nor to the significant growth of entanglement. And they're starting to be explored on platforms like organic molecules embedded in microcavities. There's plenty of things that have to be done here to make sense of this in terms of like a battery, because obviously there's limits to energy density, but also there's limits to lifetime. There's gigahertz relaxation rates in microcavities, so you cannot do very much with the gigahertz relaxation rate, even if you charge at terahertz rates. And so something that we've been doing is to try and find ways to increase the energy storage lifetime in these systems by using, for example, dark excited electronic states. But the interesting things about this system is that they have electron volt band gaps, so they can be interfaced with optoelectronic devices. Instead, for cold platforms, coherent quantum platforms, there's a lot of interesting things that can be done. The two most interesting models at the moment are the SYK model, because it displays volume low entanglement scaling. And it has been shown that it has stability at all time scales and a square root of n power advantage that is truly quantum, genuinely quantum in the sense that we discussed before. But also the quantum Ising models, because of the correlation growth that we can see at a critical point, and because we can implement it on platforms like the Wave, the QEI, Pascal, and so on. Here, of course, we need to take into account the fact that we are cooling and controlling the system. So there's an energy expenditure here as well that has to be taken into account. And usually these systems have a limited energy density. So it's more to explore the physics rather than to actually do something practical for now. But there's a couple of suggestions. One of them that I wanted to mention is the one by Kiribella about fundamental energy requirements for reversible quantum operations. And they envision a battery subsystem in order to perform quantum reversible operation on another subsystems by borrowing energy from the battery and doing this in a finite time with no production of heat. And also the one that I think is being developed at Planckian, which is a spin-off the University of Pisa by Polini and Giovannetti, where they see quantum batteries as a potential energy reservoir and actuator in a globally driven superconducting quantum computer. Yeah, okay, so with the 4 minutes that I've left, I just want to briefly outline some recent results that we got on a D-Wave machine. Here the question was, can we obtain some of these super extensive scalings on real devices? Can we see them? Or is the coherence and noise going to be an obstacle and prevent any super extensive scaling? And in this case, we wanted to focus on charging precision. So the model here is the typical easy network model with arbitrary topology in general, as long as it has the type of control that the Wave offers. We wanted to compare a local charging scheme with a cooperative charging scheme, where we always start from the collective ground state, which is just a product of all the spins down. And we want to inject as much energy as possible into the system, but also being as precise as possible at the final state. So effectively is as close as possible to all spins up, but we want to measure the energy fluctuations of that final state. The protocol that we consider is called it's a cooperative quantum information erasure protocol, where we drive the system through we start with some interaction between the qubits, and we drive the system through a critical point to develop correlations across the medium, to then bring it back to the original point. And we studied the system both numerically with the exact methods for small systems, but also with tensor network methods for larger lattices, square lattices with periodic boundary conditions. In this case, we can calculate magnetization and their fluctuations, which then lead to the precision that we want to calculate. And in the case of tensor networks, since tensor networks are not very good when we cross critical points because correlations spread everywhere, we calculated only local properties like the magnetization, and then used a Batya-Davis inequality to find a bound on the fluctuations. What you can see here is that this is 1 over this, the variance of the magnetization, which quantifies precision on the charging process. You can see the cooperative case scales like a parabola, it's quadratic, whereas the local case scales linearly like the standard quantum limit. And in fact, if you do the ratio between them, you can see that the precision of the cooperative case scales like the Heisenberg limit, so super extensively. We then scaled this up on D-Wave up to more than 5,000 qubits and fitted the results to a simple power law just to see what's the exponent alpha of the precision scaling, with alpha being equal to 1 whenever you have a standard quantum limit, and alpha is equal to 2 when you reach the Heisenberg limit. We already mentioned for the simulated results, we had alpha equal to 2 for the cooperative case. And what we can see is that alpha is still equal to 1 for the local charging protocol, whereas alpha is equal to 1.39 for the cooperative protocol, even on the noisy device. So it's not quite 2. So the deviation here can be attributed to crosstalk between the qubits, whereas the deviation here from 2 can be attributed to the noise. And so here we just proposed a simple spin flip model that we can use to tune the exponent alpha from 2 to 1 just by increasing the rate at which you have spin flips in the device. So this is it. This is all I wanted to tell you. In summary, the focal point when we study energy storage in quantum system is always about these super extensive enhancements that you might get. And the main takeaway is that there is a difference between, so to say, the quantum and the collective type of enhancements. I wanted to show you that Heisenberg limited precision is possible and is in networks, and is also possible if you have noise, as long as the noise is not too strong. And in terms of outlooks in this field, I think it's mostly concerned about finding methods to increase energy density and relaxation times, and also to put together a system that can be considered a fully operational quantum battery to think about potential applications. I want to conclude just by saying that I've already kind of seen in Lindsay's talk that there was a scaling that looks like the Heisenberg limit. The Heisenberg limit scaling at low temperature, whereas the standard quantum limit at high temperatures. And we are like familiar with this type of scaling in metrology, Grover, super radiance. And now these type of scalings are also being explored in charge transfer, heat transfer, and like I mentioned, energy storage. And if you're interested in these topics, they're all connected to energy, although in a slightly different way than the Quantum Energy Initiative. They're more looking at potential enhancements in energy-related tasks. I wanted to say that we're organizing this conference, which is second edition of the International Conference of Quantum Energy, which is also organized in collaboration with the Quantum Energy Initiative, and will be hosted in Padova next June. So if you are interested in these things, please get in touch and submit an abstract, because the abstract submissions are already open. And yeah, keep in touch, because it'll be great to connect. Thank you.
Francesco, questions?
Thanks for the talk, who should have been longer because you went a bit fast. So I have a very basic question, actually. I've not really understood the difference between collective and quantum. For me, I mean, collective, it's bosonic enhancement. When you look at decay state, you fabricate entangled state. So I don't really understand how you decipher one from the other.
So the main thing that has been, like the main question in the field was to try and understand whether or not this is a genuine advantage that you can get only from quantum systems, or if it's a property of many-body systems. So one of the suggested approaches was to compare the dynamics and the out-of-equilibrium charging process, so to say, of an identical model to the quantum model, but written in a classical sense. So with a classical Hamiltonian formalism, Poisson brackets, and so on and so forth, simply calculate the power enhancements that you get. And sometimes the power enhancements are the same, and at that point, the genuine quantum advantage is equal to 0 or trivial, so to say, because you know at that point that that enhancement wasn't given by wasn't necessarily given only by the fact that the system is quantum mechanical. I don't know if this answers the question, but this is one formalism that has been used to
but to me,
this question.
superradiance is something quantum, but maybe this is a discussion we can have.
Fair enough. Superradiance, is it quantum, or can it also be seen in classical systems? There's a plethora of papers that suggest that superradiance can also be seen in classical systems. And I don't want to take away the quantum mechanicness. Of course, it's described with a quantum mechanical formalism, but this has been a hot topic, and it's discussed in the colloquium that we wrote in detail, so that it's understood whether or not something is more quantum mechanical or just a collective property. It's connected to the development of entanglement in the system, so to say.
Okay.
Sorry, just to clarify, so the initial state of your battery and the final state, they're not entangled? It's just entangled during the dynamics that charges it?
In the examples that I gave, yes.
When there's an entanglement
There have been
advantage,
proposals
right?
where the script is reversed, where people start from states that are entangled and they might want to inject energy anyway.
Okay.
Maybe the unitaries that are used in the global sense disentangle the system at some point. But what I've discussed before, everything was a product state at the beginning and a product state at the end. I mean, entanglement was generated in the evolution.
I see, cool. And do you know of any potential applications?
That's a great question. To be honest,
useful?
Other than the things that I've discussed prior, not really. And of course, the idea is that you want to push, for example, for the organic microcavities where you have actually electron volt band gaps, which are significant, like solar cells have electron volt band gaps. As soon as you can find electronic states that have a lifetime that is long enough, maybe there is a use for it. Right now, there isn't any system that I know of that has those timescales, but people are starting to think about that as a research question. Yeah.
Thanks a lot.
Thank you.